Before we begin the second lecture, we will quickly recall what is that we did in the previous lecture. We agreed to model uncertainties in structural engineering problems using theories of probability and random processes, and with that in mind we started defining what the word probability means. There were three alternative definitions that we considered. One is the classical definition where probability of an event A is defined as ratio m by n, where n is the number of possible outcomes of a random experiment and m are the number of events favorable to the event A. This assumed that all outcomes of a random experiment are equally likely and there was no room for experimentation in this. The next definition, the relative frequency definition, based purely on experimentation. Here if a random experiment is performed n number of times and out of these n trials, if m of them are favorable to event A, then probability of A is defined as the ratio m by n, where this number of trials is taken to be sufficiently large. The problem with this definition is that it does not allow us to assign probabilities to situations where we cannot do an experiment, and what the meaning of the statement that n is sufficiently large is not mathematically very precise. So, this led to the definition of a more acceptable definition known as axiomatic definition. Here what we did was we started with certain notions which we considered as primitives, in the sense we do not define them. Terms like experiment, trial, outcome, etc., we do not offer a definition. So, experiment is a physical phenomena that could be observed repeatedly, and a single performance of an experiment is a trial, and the observation we make on performing a trial we call it as an outcome. So, with these descriptions we introduce the notion of a random experiment, which is an experiment in which we know what are all the possible outcomes of a trial, but in any given trial we do not know what exactly will be the outcome. Now, the set of all possible outcomes of a random experiment we call it as sample space. This sample space itself could be finite, countably infinite or uncountably infinite. We would like to study subsets of this sample space, and therefore we define another larger set known as event space. This is collection of subsets of omega, this sample space, on which we would like to assign a measure known as probability, which obeys these axioms, that is axiom of positivity, axiom of normalization and axiom of additivity. Now, a point in sample space we call it as sample point, and the term events are taken to mean subsets of event space on which we assign probability obeying the rules of these axioms. Now, one important thing we should notice here is that the axiomatic definition of probability does not prescribe how the probability should be measured. What it simply says is, if you are going to assign a probability to an event, obey these rules, right. It is like analogy would be like in geometry, we simply state theorems which should be obeyed by lines and curves and so on and so forth. We never talk about how to measure length of a line or a curvature of a surface, and the actual measurement issues are not addressed. The question of how to prescribe probability belongs to the subject of statistics, and at a later point in the course we will return to this question. Following the definition of probability, we introduce the notion of conditional probability, where we define probability of an event A conditioned on B. That means probability of event A given that B has occurred is by definition this ratio, probability of A intersection B divided by probability of B, and probability of B should not be equal to 0. The notion of conditional probability, based on this notion we defined what is meant by independence of two events. we say that events A and B are independent if probability of A intersection B is probability of A into probability of B. This would also mean that probability of A is not affected by the occurrence of event B. We briefly talked about total probability theorem and Bayes theorem. There will be occasions for us to use this, so I would not like to elaborate on this at this stage. In today's lecture, I would like to introduce the notion of a random variable. That is what we will begin today. Again, we will return to this schematic description of axiomatic definition of probability. This is the event space, this is the sample space, this is the this is the random experiment, the sample space, event space and the probability. Now, we define a function, random variable is a function that is defined from sample space into the real line such that means for every element in sample space we assign a number on the real line such that the probability, we would like to consider the set of all omega, omega is a point in sample space such that x of omega less than or equal to x is an event. In the sense, for this set we would like to assign a probability. So, I need to clarify what this set means. We also impose certain restrictions stated here. Now, let me clarify what is the meaning of this set. So, to do that we will consider a simple example of die tossing. So, the sample space here is 1, 2, 3, 4, 5 and 6. This could as well be red, yellow, blue or any 6 colors as well, but it so happens that I am on the die we are seeing those dots and I am counting the number of dots. I define now a function x of omega I as 10i, where I is 1, 2, 3, 4, 5, 6. That means, if this is a sample space, I map 1 to the point 10, 2 to the point 20 and so on and so forth, 6 to the point 60. So, this mapping defines the definition of random variable. I mean, this provides the definition of random variable. Now, let us now look at what is the meaning of the set x of omega less than or equal to x. We are tempted to interpret this as a part of the real line, but that is not what exactly we mean. We would like to interpret this as a subset of omega and therefore an element in B, because this is a finite sample space on which we would like to assign probabilities. Let us consider what is x less than or equal to 40. So, 40 is here. What are the events, what are the points in sample space which lie to the left of these points? Okay? That is 1, 2, 3, 4. The subset of sample space, namely 1, 2, 3, 4 is this set. It is not the interval from minus infinity to 40. You should not interpret that way. It is actually subset of sample space where elements in that are mapped to the left of this point. Similarly, what is x less than or equal to 5? So, you look at 5, are there any points in sample space which are mapped to this line? No, therefore, this is a null set. Now, you look at x less than or equal to 100. So, 100 is somewhere here, 100 is somewhere here, and we see that all these points 1, 2, 3, 4, 5, 6 are mapped to the left of that point. So, therefore, x less than or equal to 100 is nothing but the sample space itself. Okay. Now, one more example, so 10 will not be in that, 20 will be in, 30 will be in, 40 will be in and 50 will be. So, that means 2, 3, 4, 5. Now, this set x of omega less than or equal to x, for sake of simplicity we write it as x less than or equal to x. We omit this omega is a sample point in the sample space, that we will not write explicitly as a convention. That is simply. Now, what is the need for introducing the notion of a random variable? It will become clear as we go along, but at this stage a first order description of that would be that it enables us to deal with sample space which is not numerically valued. For example, you toss a coin, you get head or tail, they are not numbers. So, you can as well say when I get head I will call it as 0 and when I get tail I will call it as 1. That is the definition of random variable for that random experiment. By talking about numbers, we immediately would be able to quantify the uncertainties. Okay? Instead of talking about head and tail, since I am talking about numbers, I would be able to quantify uncertainty in some sense. You would also see later that the introduction of random variable also forms the basis on which we talk about descriptions such as mean, standard deviation, covariance and so on and so forth, which you might have heard about, but we will now make the meaning of these terms precise in due course. Now, we introduce a function known as probability distribution function. The notation we use is Px of x. Now, x of omega is the random variable. The probability distribution function is notation is this, that is what I am following. This, as we are writing here, this is probability of x of omega less than or equal to x, where x itself takes values from infinity. This x that I am writing as a subscript refers to this random variable. This lowercase x I am writing refers to this state. This is a random variable. This function, as we vary x, if we were to plot Px of x versus x, that function is known as probability distribution function. Again, this omega we are not going to write when we write probability distribution function, that is the dependence on omega is not explicitly displayed. Now, what are the properties of this probability distribution function? It is essentially a probability, therefore, it should be a number between 0 and 1. It cannot be negative, it cannot be greater than 1. Px of infinity is what? X less than or equal to infinity. X less than or equal to infinity is nothing but the sample space. Probability of sample space is 1 because that is the axiom. Px of minus infinity is what? It is probability of x less than or equal to minus infinity. This event x less than or equal to minus infinity is nothing but a null set. Probability of null set is 0, which is again one of the corollaries that we saw in the previous lecture. An important property of probability distribution function is that it is monotone non-decreasing. That means as x is increased, the probability distribution function can remain constant or it can increase, it cannot reduce. Okay? Why is that so? So, if we consider 2 points x1, x2, the event x less than or equal to x2 can be written as x less than or equal to x1 union x1 x greater than x1 and less than or equal to x2. These two events are mutually exclusive. Therefore, the probability of x less than or equal to x2 can be written as probability of x less than or equal to x1 plus the probability of this event. this probability itself is a number between 0 and 1. Consequently, if I drop this term here, it would mean probability of x less than or equal to x2 at the most can be equal to probability of x less than or equal to x1. By monotone non decreasing, this is what I mean. Okay. So, typical probability distribution function can be like this. This is okay, but it cannot be like this. Okay. Now, there is one more property that we need to understand. I will elaborate this shortly. The probability density function is right continuous. I will explain that slightly later. We will continue now by considering an example. We will again return to this example of die tossing. This coin tossing and die tossing experiments are time honored simple experiments to learn about probability, that is why I am using them. So, we again consider this die tossing experiment. The sample space is 1, 2, 3, 4, 5, 6. The random variable we define as x of omega as 10i. So, again different values. Now, let us plot the lowercase x here on the x axis here and go on assigning values to x. Suppose x equal to 0. What is x less than or equal to 0? It is a null set. Therefore, probability of x less than or equal to x is 0. That means at 0 I should plot 0. How about minus 100? X less than or equal to minus 100 is 5, null set, probability continues to be 0. Now, what happens at 600? Probability x less than or equal to 600 is probability of the sample space. Therefore, that is 1. That means here it is 0 and as x becomes large it is becoming 1. Now, how about 5? It is still 0. How about 10? X less than or equal to 10 is we capture the first event here getting 1, and if the die is fair, that probability will be 1 by 6. We will use the classical definition. So, that at x equal to 10, therefore, the curve jumps from 0 to 1 by 6. How about at 11, x equal to 11? So, 11 is here. So, the only event is 10, only event is 1, right. The probability therefore continues to remain constant till we encounter the point 20. At 20 what happens? X less than or equal to 20. So, in that basket there will be one more event 1, 2, right. So, these getting 1 and getting 2 are mutually exclusive, therefore, union of 1 comma 2 is probability of 1 plus probability of 2. So, I will get 2 by 6, that means from 1 by 6 it now jumps to 2 by 6. So, as we continue you can assign 20, 22, 35 etc. For example, 35 we are here. So, there are 3 sample points 1, 2, 3, therefore, probability is 3 by 6. So, at 35 I get 3 by 6. Now, you notice now I am putting a dark spot here and a circle here. At x equal to 20 the probability distribution function is discontinuous. As a convention, whenever there is a discontinuity we would report the value of probability distribution function from the limit from the right hand side. That means, probability distribution function at 20 we should report it as 2 by 6, that is a convention again. Okay. So, this is actually the probability distribution function. You can easily see now all these numbers are between 0 and 1 and it is monotone non decreasing. There is nowhere the probability distribution function actually comes down. Now, in further representations we will not bother to write these dot and these circles, eventually we will stop writing that. If we were to do that we will plot the same graph in this manner, it is like a staircase function. This is the probability distribution function of this random variable. Now, if we are given this picture, you should notice that whatever we need to learn about this random experiment is encapsulated in this graph. Okay? That will become again clear as we go along, you should notice that right away. Now, one more experiment. Let us consider the experiment of arrival of a train on a platform. So, let capital T be the arrival time. let any time instant in the interval t1 to t2 be equally likely. So, the random experiment here is you observe when the train arrives on the platform. Now, what I will, therefore, the sample space is the interval t1 to t2. So, it will not arrive before t1 and it would have certainly arrived after t2, okay, right. Now, let t be the random variable which denotes the time of arrival. So, t belongs to the interval t1 to t2. Now, we will begin with a simple model where the interval t1 to t2 is divided here. Let us t1 to t2 is divided into two intervals. For example, this is 10 o'clock, this is 11 o'clock. I will say 10 to 10:30 is my slot 1, 10:30 to 11 is my slot 2. So, what is the probability that train would arrive between 10 to 10:30 is 0.5. So, this is a 0.5 I write here. Now, what is the probability that capital T is less than this point? It is train arrival in slot 1 and train arrival in slot 2. Therefore, the probability is 1. So, okay. If you are to make 4 slots, okay, you will get number of. We will now consider another example. The random experiment here is as follows. Consider time of arrival of a train on a platform. So, let us denote by capital T the arrival time. Let us assume that the train arrives on the platform any time during the interval t1 to t2. So, the sample space here is the interval t1 to t2. The random variable is the time at which the train arrives, that itself is a number. So, it is t1 to t2. Now, so t be the random variable which denotes the time of arrival. Now, what we will do is we will now focus on this sketch. I am dividing the interval t1 to t2 into two intervals, two sub intervals, and now I will consider the random experiment where I will observe if train has come in slot 1 or slot 2. For example, this is 10 o'clock and this is 11 o'clock. The first slot is 10 to 10:30, second slot is 10:30 to 11. Now, what is the probability that train arrives, would have arrived at say 10:15 is 1, is half, because the probability that train would arrive between 10 and 10:30 is half. So, this is half. So, if you consider a time instant between 10:30 and 10:45, the probability will be 1. So, here the sample space has two outcomes. Now, the interval t1 to t2 can now be divided into 4 such slots. Here this jump in probability distribution function is 1 by 4. So, as we divide this interval into larger number of sub intervals, in the limit, for example, if I take n discrete time segments, then we can take capital T as Tn if the arrival is between Tn to Tn plus 1. So, typically the probability distribution function of this discrete random variable would be a staircase of n steps. At each step it will increment by T2 minus T1 by n. Now, in the limit of this n becoming infinity, you would see that this staircase would now become a ramp, and this probability distribution function now corresponds to a random variable which we call as being continuous. This is a continuous random variable. The sample space here is the real line T1 to T2. Okay. Thus, we can now see that we can classify random variables into 3 categories. One is discrete random variables, other one is continuous random variables, and there is a third category known as mixed random variable. A working definition for these random variables could be this: in a discrete random variable, the probability distribution function proceeds only through jumps. Any increase in probability distribution function is only through a jump. Whereas in a continuous random variable, the probability distribution function proceeds without any jumps. whereas in a mixed random variable the probability distribution function proceeds with both jumps and continuous segments. For example, this is the probability distribution function of a mixed random variable. So, in this segment it is increasing continuously, and at this point there is a discrete jump, and then it continues to increase continuously. So, this is in a general type of random variable there could be several such jumps, and there could be several such continuous segments. Now, again let us return to the point where there is a jump. You see here I have drawn a circle here and a blob here. So, if I want to know the probability distribution of the value of the probability distribution function at this point, this is the definition that we will adopt. We will take a point which is x plus epsilon, where epsilon is positive, that means we approach from this side, and this is the number that we report as probability distribution function at this value. Although this is also a I mean there is a discontinuity here. If you approach from left you will get this, from right you will get this, but as a convention we assume that probability distribution function is right continuous. We now introduce another description of a random variable, namely probability density function. This is written with a lowercase p. The subscript is again a capital letter X and the argument is a lowercase x. The definition is the probability density function of random variable x evaluated at the probability density function of random variable x evaluated at this lowercase x is actually the slope of the probability distribution function at x. It is by definition the derivative of the probability distribution function. So, from this you get probability distribution function itself as minus infinity to x px of u du. That is the relationship between the two functions. What are the properties of probability density function? Now, we have the value of probability distribution function at infinity is actually the probability of sample space, and that should be equal to 1. Therefore, if you evaluate this integral minus infinity to plus infinity px of u du, it should be equal to 1. That means the area under probability density function must be equal to 1. Actually this statement is a consequence of the axiom that probability of sample space is 1. It is actually the statement of one of the axioms. If you consider now probability of this event x greater than or equal to a and less than or equal to b, this is the area under the probability density function between a and b, right. So, that is why this function px of u is called a density function. You multiply by the length of the segment and integrate over a to b, you get the probability. The probability density function itself is not a probability, its area under the probability density function is a probability. Now, this can be seen more clearly here. This is a probability density function. If you consider 2 point a to b, the area under this curve is a to b px of x dx. This is probability of a x greater than a less than or equal to b. Now, if you shrink b to a and consider an infinitesimal strip here x to x plus dx, this area is px of x dx, and this is a probability, okay, of x lying between x to x plus dx, right. Now, this probability is positive, and since dx is positive, px of x must be positive or non-negative to be precise. That means probability density function cannot be negative because probability measure itself cannot be negative, and the area under this curve must be equal to 1. Both these statements are actually statements of axioms of probability. There are other terminologies that you may come across if you read certain textbooks. For example, probability of x equal to k is written as pk, and as k is varied, and if you plot now this function as a function of k, this is also known as probability mass function, PMF. This probability distribution function is also known as cumulative probability distribution. Some authors call it as CDF also. But I will stick to the notation. Capital PDF is probability distribution function, lowercase pdf is probability density function, and I will not use these terminologies probability mass function and cumulative distribution function. Before we proceed further, we need to now digress a bit, and I need to introduce the notion of a Heaviside step function and a Dirac's delta function. Heaviside step function is shown here. U of x minus a is said to be the Heaviside step function if this is at a, for x less than a this function is 0, and for x greater than a this function is 1, and at x equal to a we take the average of the right and left limit, and by again we call it as half. That is the definition of a Heaviside step function. It is also called just simply as step function. Now this is quite a useful function to represent functions like this. For example, if you consider a box function, that is f of x is 0, from 0 to a, at a there is a jump, and this is the box. How can I write this in terms of step functions? We can write this function as being equal to minus b. This is nothing but u of x minus a, this is u of x minus b. So if you deduct this from this, you will get this function, and we write it as u of x minus a minus u of x minus b. Now what we will do is we will use this representation to describe what is known as Dirac's delta functions. So what we will do is we will start with a function, let us call this point as a and this as f naught, and this is the origin. Now what I will do is I will go on reducing a, but at the same time this area is what? F naught into a. I will keep the area as constant equal to 1, and I will go on reducing a. So what I will do, for instance, I will now say a becomes a by 2, this will become 2 f naught. So what is the area under this curve? 2 f naught by into a by 2, it is f naught a. Okay. Now suppose this becomes a by 4, suppose this is a by 4, this will be 4 f naught. So the area would be still 1. So in the limit of a going to 0 and f naught into a going to 1, what would happen to this function? It will be a kind of a spike at 0. Now let us look at these details here. F of x is f naught into u minus x, x minus a, that is this function, that is this. Now I am considering the limit a going to 0 and f naught a going to 1. So I will rewrite this as f naught into a divided by a. So as f naught into a goes to 1 and a goes to 0, you are looking at the derivative of u of x. This u of x minus u of x minus a divided by a, as a goes to 0 is nothing but du by dx, and f naught a goes to 1. Therefore f of x now becomes this function, and this we call it as Dirac's delta function. and we represent this as simply a spike like this. The definition of this function is as follows: Dirac delta of x minus a equal to 0 for any x which is not equal to a, but at x equal to a itself we do not define this function. We simply say the area under this curve is 1. Okay. There is another property of Dirac's delta function which we will be needing. If you take the integral of f of x into delta of x minus a dx, it will be f of a, and this property we already saw. The derivative of a step function is Dirac delta function. Okay. So, some of this we will be using quite often later in the course. There is one more small example that will help us to understand the step function and Dirac delta function further. So, I consider now a box which has a step here. This function can be written as alpha into u of x minus a, that is this part, plus beta into u of x minus a minus u of x minus b, that is the second part. So, we are able to write this type of functions in terms of step functions. Now, if we were to need the derivative of f of x, although the slope is 0 everywhere, but at points of discontinuity we cannot differentiate that. So, we represent the derivative in a formal way in terms of this Dirac's delta function. Suppose if we differentiate this with respect to x, this is Dirac delta function, this is Dirac at x minus a, this is Dirac delta at x minus a, Dirac delta at x minus b. Okay. Now, why we should need, why we will, what is the use of this? I will come to this shortly. Now, I remark that random variables help us to quantify uncertainties. Now, the description of a random variable, so far we have derived, we have introduced the notion of a probability distribution function and a probability density function. If you know probability distribution function, you can get probability density function. Similarly, if you know probability density function, you can get probability distribution function. So, a complete description of a random variable is through its probability distribution function or through its probability density function. However, you should also understand complete description of a random experiment itself is through sample space, event space and the probabilities. That triplet probability, the sample space, event space and probability measures now are encapsulated in probability distribution function or probability density function. Now, just as we encounter certain types of functions in our engineering practice or in modeling physical world, like sine functions, cosine functions, exponentials, logarithms, etc., these are commonly encountered in modeling. That happens because these type of functions are obtained by solving the governing physical laws. For example, when a pendulum swings through small oscillations, the sine and cosine functions emerge naturally. In a diffusion type of model, exponential functions emerge naturally. In a similar fashion, when we talk about uncertainties, there are certain kinds of uncertainties which keep occurring frequently. That would mean there are certain types of functions, that is random variables, which keep recurring frequently in modeling. Now, I will now consider some examples, for example, models for rare events, models for sums of uncertainties, models for products, models for extremes, the highest and the lowest. We are interested in highest extremes of environment which acts as inputs to our engineering systems. For example, floods and drought are extremes of certain climatic conditions. We are interested in strongest earthquakes and lowest strength in the structure, highest wind speeds, right. So, when we talk about structural strength, we are interested what is the weakest point. When we are interested in loads, we are interested in the highest points. Similarly, we are interested in models for waiting times. One example for a waiting time is the life of the structure itself. How much should I wait till its structure collapses? If the structure is exposed to uncertain effects and it has uncertain properties, its life also is uncertain. So, while introducing random variables, it will be quite useful if we look at random variables from a certain physical perspective like this. There is another important property of random variables that we should understand. These are associated with limit theorems. So, these are very important results in probability theory. I will come to that in due course. So, we will be now going through some of this in sequence. The first random variable that we will be looking for, that we will be studying, is known as Bernoulli random variable. In a Bernoulli random variable, the underlying random experiment has only two outcomes, call it as success or failure. It could be, for example, testing a cube in a laboratory and see whether the compressive strength exceeds a threshold value or not. There are only two outcomes here. Toss a coin, you get head or tail. You appear for an exam, you pass or fail. There are only two outcomes. We call probability of success, we plot the random variable. Success we map to 0, failure we map to 1, and probability of success we call it as P, and therefore probability of failure must be 1 minus P. So, what is the probability distribution function? Here this is the origin 0, 0, this is 1. So, the climb here is P and the climb here is 1 minus P. So, this is a probability distribution function. Okay. So, what can you say about this probability distribution function? It corresponds to a discrete random variable. Okay. So, the sample space here has two outcomes. So, it is a finite sample space and this is a discrete random variable, and if you want to construct its probability density function, you have to use the representations using step functions. So, you get one Dirac delta function at the origin, which is P, and other Dirac delta function here where the climb is 1 minus P, and that is what appears here. So, this is the probability density function, this is a probability distribution function. So, if you look at these plots, all the underlying features of your modeling of random experiment are encapsulated here. It is in this sense that I say that this helps in quantification. Okay. Now, the probability distribution function is P into U of x plus 1 minus P into U of x minus 1. Now, the density function is the derivative of this P into Dirac delta plus 1 minus P into Dirac delta x minus 1. Is the area under the curve equal to 1 of this? You find the integral. This is P delta x plus 1 minus P delta of x minus 1 dx. Now, P into delta x, area under that curve is P, 1 minus P, area under this curve is 1 minus P. So, P plus 1 minus P is 1, right. So, all axioms of probability are respected. So, this is how we describe a simple random variable like Bernoulli random variable. This Bernoulli random variable is an important random variable in the sense it forms the building block for constructing many other random variables. So, we call it as binomial random variable. The sample space here consists of repeated Bernoulli trials. You toss a coin for n number of times and ask the question how many heads you have obtained. That means the random experiment here consists of n repeated Bernoulli trials. We make certain assumptions here. The random experiment consists of n independent trials. Each trial results in only two outcomes, success or failure. That is what I mean by saying that the trial is a Bernoulli trial. Probability of success remains constant during all trials. Suppose you are tossing a coin, at every toss of the coin the probability of getting head should remain the same. Then we define x as a number of successes in n trials. So, how many successes are possible? You may not succeed at all or you may succeed all the time. So, it is 0, 1, 2, 3, n. The probability of x equal to k, we will shortly show this, can be shown as nck pk 1 minus p n minus to the power of n minus k, where k takes values from 0, 1 to n. Now, why this random variable is called binomial random variable? The reason is, if you were to find out probability of sample space, that means you have to sum this probability from k equal to 0 to capital N. In doing so, you utilize the binomial theorem, which says that p plus q to the power of n is given by this. We utilize this in showing that this description obeys one of the axioms of probability, namely probability of sample space is 1. Therefore, the name binomial random variable. How do we get this probability, probability of x equal to k to be this? We will see now in a minute. Now, to derive this description, we will consider a sequence of n trials resulting in k successes. I have tossed a coin say 30 times and I have got 8 heads, right. So, I am trying to describe that. Now, occurrence of k successes implies the occurrence of n minus k failures. If I got 8 heads, I should have got 22 tails. Probability of occurrence of one such sequence is p to the power of k successes and n minus k failures, and all these are independent, therefore, I multiply these probabilities, p to the power of k 1 minus p n to the power of minus k. How many such sequences are possible? How many ways I can draw k objects from a pile of n objects, nck, and these sequences are mutually exclusive. If one sequence occurs, the other sequence cannot occur. So, the intersection is a null set. Therefore, if you now look at probability of x equal to k, I can use now the third axiom of probability and add all this up. So, I get nck p to the power of k 1 minus p n minus k. This is how the probability mass function, as we call for this quantity, is derived for a binomial random variable. Now, what is the probability distribution function? It is probability of x less than or equal to m, k running from 0 to m, this, and probability of x less than or equal to n is actually this summation, and you can show this to be 1 by virtue of binomial theorem. As I said, this is why this random variable is called a binomial random variable. Now, there are two parameters in this description of random variables, this random variable, namely the number of trials and the probability of success on any given trial. So, we say that a binomial random variable has two parameters, capital N and P. This is again a discrete random variable. The sample space is finite because there are only n plus 1 outcomes, 0, 1, 2, 3, 4 and up to capital N. Okay. Now, a plot of a binomial probability distribution and density function of a binomial random variable where capital N is 10, you can plot that function and it appears as a staircase. This is the probability distribution function, and associated with this there are spikes corresponding to the these jumps, and this is the probability density function. Now, based on binomial random variable, we can define what is known as a geometric random variable. Now, the random experiment here is as in binomial random variable. That means, you will go on tossing coin n number of times and see how many heads you get. But the observation we make here is this random variable is how many trials are needed for the first success. That is the random variable here. How many times you need to appear for an exam before you pass or before you cross a certain threshold. Now, how do we construct this probability now? Now, let us consider that the successes occurred in nth trial, the first success. Probability of first success in nth trial is, if you have got head on 30th trial, you would have got tails on first 29 trials, okay, because 30th trial is the first success. So, probability of success on nth trial intersection failures on the first n minus 1 trials. If you moment you get a head, you would stop the experiment, right. So, here what is therefore probability of n equal to n it is 1 minus p to the power of n minus 1 into p. Now, what happens if you sum the states are here 1, 2, 3 up to infinity. So, what can you say about this random variable? This is a discrete random variable and it has countably infinite sample space. You may never succeed. So, you may have to go on tossing the coin. The coin is so bad that you will never get a head. So, the number of trials can extend all the way up to infinity. So, it has countably infinite sample space. Now, is the axiom of one of the axiom probability of sample space is equal to 1 or not? How do we check? You have to sum these probability from n equal to 1 to infinity. If you do that, you get this, and for the axiom to be obeyed, this must be equal to 1. So, to illustrate that, let us consider p equal to 0.6. So, what is this? Summation n equal to 1 to infinity 1 minus p n minus 1 into p. This is this, and if you expand and write, this is 0.6, 1 plus 0.4, etc., etc. So, the number in the bracket is a geometric progression, and you will see that if you use the result of sum of a geometric progression, you will see that this area is 1. So, the name geometric random variable now arises from the property that we are to show that probability of sample space is 1, we are using a property of a geometric progression. So, that is why this term geometric random variable. Now, this geometric random variable is a very useful modeling tool if we are trying to model lifetimes. Suppose at a point on the structure we say the structure has failed if stress exceeds a threshold, some threshold. So, every year or every time unit I monitor how many years I have to wait till the response of the structure exceeds a threshold. So, these are typical questions that we need to ask, and you can immediately see that this geometric random variable has relevance in answering such questions. This is one plot of the probability distribution function of geometric random variable, where the p, that is probability of success on any trial, is taken as 0.4, and here again you will see that this is a discrete random variable and it has countably infinite sample space. So, there are infinite number of these small steps, and eventually this distribution function reaches 1. The derivative of this, again it does not actually exist, but in terms of Dirac delta function we can represent, and we get a spike at these places where there are jumps. So, this is the probability density function, this is the probability distribution function. There is another generalization of geometric random variable. We define Wk as number of trial to the kth success. In a geometric random variable we waited for first success, now here we are waiting for kth success. This could be relevant, for example, if you are modeling fatigue phenomena and so on and so forth. You can show that this Wk, the probability of Wk equal to W is given by this expression. This can be shown using properties of binomial random variables. Next, we move on to models for rare events. Here we come across what are known as Poisson random variables. The story here is as follows. Here we are looking for occurrence of an isolated phenomena in time or space continuum. We will have a simple example in mind. Suppose you are looking at number of goals scored in a football match. So, you are looking at isolated events in time continuum. Okay? If you are looking for a defect in a yarn, okay, you take a yarn and you inspect for defects, you are looking for isolated phenomena in space continuum, one dimensional space continuum. Similarly, if you are looking for typographical errors in a manuscript, you are looking for isolated events in a two dimensional continuum. If you are looking for a defect in a solid, you are looking for an isolated event in a three dimensional continuum. If you are looking at a time history of a stress at a point, one of the components of stress at a point in time, and you are looking at the event that it exceeds the elastic limit, okay, during the lifetime of the structure, you are looking at isolated phenomena in time. Now, if you look at, for example, goals in a football match, we cannot put an upper bound on the number of occurrences. We cannot say in a football match goals more than so many are not possible, any number is possible. But in reality the actual number of occurrences is relatively small, right. You will not hear of a football match where 800 goals are scored, maybe 4 goals, 5 goals are okay. If these conditions are satisfied, this counting random variable where we count the number of these isolated phenomena follows what is known as a Poisson distribution. It is a random variable, it is an integer valued random variable, it has countably infinite sample space, and the probability mass function probability x equal to k, it can be shown that it is given by exponential of minus a to the power of k divided by k factorial, where k runs from 0, 1, 2 up to infinity. We can show that the sum of this, that means again whenever we introduce a probability distribution function, we need to check whether the axiom of probability is obeyed or not. So, if we sum this, if we sum this quantity from k equal to 0 to infinity, you can show that this sum becomes 1. So, we will conclude this lecture at this point, we will continue with this in the next lecture.